So first of all, I will build the system on Quartus. So click compile to compile the system, and the result shows that the project is successfully compiled. So next I will use RTL viewer to see the block diagram of the design. So as we can see here, there are three components on the system. The first component is the column processor. The second is the row processor, and finally the scale unit. As we can see that the column processor receives 4 inputs from matrix column data and provide 4 outputs for the row processor. The last component, scale unit, will produce the 4 final outputs. So we can take a detailed look at the column processor. Inside it has 2 subsystems. Each handle 2 outputs from a column, so 2 subsystems will handle 4 outputs from 2 columns. So inside each subsystem, there has 2 cores which implement 2 steps of lifting scheme. Here is a detailed view of step 1. And similar to the column processor, the row processor has 2 subsystems, and each will implement 1 row of matrix data. Inside the row subsystem, there is also 2 cores for implement 2 steps of lifting scheme, just like the column processor. And the detailed view of step 1 is shown here. The scale unit will receive output from row processor and produce the 4 final outputs, which can be used to display an image. And here is the detailed look of the inside scale unit system. So in order to run the project, firstly we must prepare an image matrix data. We can use MATLAB to achieve a matrix from an image. So here we use a Lena image. This is a 512 grayscale image. We read the image to a MATLAB variable. So because in ModelSim we can only read row data from text file, not column. So in MATLAB we can use transpose function to transpose the matrix, and it will make the implementation of matrix in ModelSim easier. Here we transpose the matrix I to matrix A. We can then open the matrix A. And next we will copy the content of matrix A to a text file. And this is the input matrix for the project in the ModelSim. So here I will give some description about the testbench file. As we can see, there are 3 declared components in the system: the column processor, the row processor, and the scale unit, just like the Quartus system. Here I declare the input matrix, which I just created from MATLAB, and we use readLine to read data from a matrix row. And here I declare 4 output file to store the 4 output matrix. The 1.txt is the the file store LL matrix, and we use write line to write the data to a file. In this part, I will give some demonstration of the system on MonoSim. As we can see here, there are three components correspond to the testbench file. And here is the column processor had two subsystems, and inside subsystem there has two cores for implement two steps of lifting scheme. And in the wave window, I show the function of step 1. Here I just add some basic signal of the core. We can run 100 nanoseconds to see the performance of step 1. And here, these are two input from a matrix column. After one block cycle, the input is calculated and stored in the 3 resistor. And next, the value of 3 resistor is computed and stored on the R1, R4 and R5. And finally, the output is calculated after the 3 clock cycle. And here is the detailed view of row processor. So similar to column processor, the row processor had two subsystems, and inside each subsystem there has two cores for implement two steps of lifting scheme. And here I add some basic signal of the core. The input from row column processor and the output. Here we can run for 900 nanoseconds to capture the output data in step 1 of row processor. As we can see here, the two inputs is provided. After one block cycle, the calculated value is stored in the 3 register. However, different from the column processor, the row processor has to buffer memory to store intermediate data. And because the input of row processor is not continuous, so the output cannot provide in a short time like a column processor. It had to wait for half of n cycles, and we have output from row processor. And here I will run the project in full time for about 136 microseconds, and the final matrix can be achieved. After the simulation ends, we will have the 4 matrix stored in the 4 text file. And here is the 4 output text file that contains the LL, LH, HL and HH matrix for 2D DWG. So as we can see here, the output coefficient is very messy, so we need to edit it so that we can input the matrix to MATLAB easier. And we can save the file as 1D, one MATLAB file. And here we have 4 MATLAB test file for display image. So in MATLAB we can access to the 4 created text file and input it to MATLAB as a variable. In MATLAB we need to transpose the matrix back so that we can see the image correctly. Here we can see the linear image of LL matrix, just like what we did in the MATLAB last semester. So it can be observed that the 4 boundary has no artifact because symmetric extension has been used. And we can show another matrix from ModelSim result. So here is the image of LH matrix. So in comparison with the LL matrix, this image is very blurred. I also create a version of technique that would have no symmetric extension. So here we have the 4 output text file, just like we did for symmetric extension. In this technique we use zero backlinking extension. So we input the 4 text file and show the image from the LL matrix. So as we can see here, the matrix is similar, but at the 4 boundary it have a lot of artifacts. So with this kind of extension, the compressed image cannot be reconstructed. Therefore, symmetric extension is the suitable technique for DWT.